Okay, so we are looking at today more specifically what enthalpy is and figuring out a couple more ways to determine enthalpy in heat of a reaction. Right here I have a little definition of a state function. Enthalpy is an example of a state function. Delta H is heat of a reaction. And it's a state function because let's say I'm looking for delta H and I have reactant energy and product energy. Okay. Regardless of the path that I take to get from one to the other, my delta H is going to remain the same. So I could do this, and my delta H looks kind of like this. Or I could take this path. Would my delta H be any different? Nope. That's what a state function is. Okay? A property that depends only on the state of a system, not on the path, okay, to get the system to the particular state. Hess's law is the law that says in going from a particular set of reactants to products, specifically reactants to products, the enthalpy change is the same regardless whether we do it in one step or multiple steps. Okay? So in our process of learning the different ways to find enthalpy, you're going to see we have different methods which take different amounts of work. So the ways to find enthalpy. Yesterday we learned one way. How did we find enthalpy yesterday? Calorimetry. Okay, and today I'm going to show you two different ways. One is the use of stoichiometry. If you've been doing your homework, you would have seen these stoichiometry problems, okay? And there's actually one on the quiz, so that's why I'm doing the lecture before the quiz. And then the other way that you're going to learn today, I call it the Flippy Thing. And then this morning, Breck wants me to change thing to thang. So the Flippy Thing. And then the fourth way we're going to do tomorrow is the use of the Big Mama equation. Okay, and Big Mama is up there in her curlers, she's in a house coat, holding her soda. Okay, so we'll introduce her tomorrow. So our focus today is stoichiometry and the Flippy Thing. Before we can really delve into these big time delta H calcs, you need to understand what it means to be standard state. Another way we say this is standard conditions. Standard conditions are going to be different for thermochemistry, electrochemistry, and all that compared to gas laws. So when you see a little circle like that on a delta H, that means standard conditions. And standard conditions for everything but gas laws is 25 degrees C, which is 298 K, and 1 ATM. All right, those are standard conditions. So now let's move on. There's two definitions you need to know. First is called the heat of formation. Heat of formation. Heat of formation is the heat associated with forming 1 mole of any substance from its elements. Okay, these are in your notes. Notice in each of these equations, we are forming 1 mole of a substance from its elements. In cases like heats of formation, it's okay to have fractional coefficients. You will need to be able to know how to write a heat of formation equation. So, I don't know, I'm going to pick something. Magnesium phosphate. Whatever. So magnesium phosphate is this formula. Okay. I want to form 1 mole of this. So to write an equation, I'm going to have to form this from its elements, but not change the coefficient in front of it. So how many magnesiums do I need? 3. So I'm going to write 3 Mg plus, how many phosphorus? 2. Notice I'm breaking up the polyatomic. It's from its elements. It's not from its ions, from its elements. And then O doesn't exist as O. It exists as O2. So how many O2s do I need? 4 O2s. And that would be a heat of formation equation for magnesium phosphate. Now notice next to all these heat of formation equations, you've got these numbers. Those numbers are the heat given off or absorbed, depending if it's positive or negative, whenever 1 mole of that substance is formed. So everyone take a look at the very last page of your notes. You're going to see a big table. You'll probably recognize this from last year. You've got delta H, delta S, and delta G on that table. All your delta H's, these are all heats of formation. So every single number on that table is associated with forming 1 mole of that substance. So find an element alone, like oxygen or sulfur or iron, whatever. What do you see as a heat of formation of those? 0. Why are they 0? They're already formed. They're free, natural occurring elements, so they don't have a heat of formation. Okay? Pay attention to your units whenever you use this chart. This particular time, we're only doing delta H. Well, we're going to pull in S and G later. But for now, since we're only doing delta H, just look, it's kilojoules per mole, right? So that's what we're going to focus on as our units. And if I were a really mean teacher, I could say, hey, take that table and I want you to write a heat of formation equation for every single compound on there. I'm not going to do it, but you see how you can then form each one of those from the elements. And the heat on there is the heat that is associated with that reaction. Okay, you got it? All right. As long as you understand that, you're good to go. So let's jump into a different definition. Similar to heat of formation, it's called heat of combustion. Heat of combustion is symbolized, looks like this. And if it's standard conditions, we'll have a little circle. But heat of combustion is the heat associated with the, you'll have to jot this down, there's no separate part for it, just jot it down on the notes somewhere. The heat associated with the combustion of 1 mole of a substance. So writing these equations in the heat of combustion way is just as easy as heat of formation, but instead of forming 1 mole of something, we're going to combust 1 mole of something. And so the 1 needs to stay in front of the combustible material. So say I were to write a heat of combustion for CH4. Let me erase it and do it neater. CH4. I am going to combust it. And what do I make? Come on, guys. CO2 and H2O. Now, because it's by definition a heat of combustion, I have to have a 1 in front of that thing that I'm combusting, which in this case is methane, and I don't change it. If I need fractional coefficients to make it happen, that's great. I do my O's last. I have 1 C, 2 H's. How many O's? 4 O's, so I need a 2 there, and that's balanced. That's an easy one. But sometimes we get ones that are a little bit more difficult. C6H6, for instance. Okay. This could be cyclohexane. We're going to add that, and we make the same products, but this time the balancing is going to be a little bit more difficult, more challenging, and we're going to have a fractional coefficient. So again, we have to have a 1 in front of there. I need 3 times 2 H's, and I need 6 C's. How many O's does that make me need? 15 O's. Well, I can't do, what would I need to be 15 in fraction-wise here? 7.5, but fraction would be what? 15 over 2, exactly. And that would be my heat of combustion equation for cyclohexane. Okay? Or it could be a hexene as well. This could be multiple things. There's lots of isomers for that. So do y'all have any questions? Okay. So now we're going to put this into action a little bit here. It says the heat enthalpy for the formation of Na2O is shown below. So whenever you see a problem like this, there's a stoichiometric relationship. Okay. For every 4 of these and 1 of these and 2 of these, I give off that many kilojoules. So I can go stoichiometrically from any one of the reactants or products to find joules. So looking at this one, we're forming 2 moles. Here it says what is the amount of heat released when 1 mole is formed. what would it be? Half of it, right? Now let me just show you, that's easy. That's an easy one, but let me just show you how you can do it if you didn't quickly recognize it was half. You start with whatever's in your problem. We're going to start with the 1 mole of Na2O. The reason it works is because we have a stoichiometric relationship from there to there. So for every 2 moles from the balanced equation of Na2O, I have negative 828 kilojoules. Okay? And I'm going to say, well, I'll change in a second, but all of these delta H's should really have per mole of reaction on them. All right, so that's where the whole dividing by 2 comes from. So it's negative 1.414 kilojoules. And it should be kilojoules per mole of reaction. So that one's pretty simple because of the whole stoichiometry thing and because of the 1 to 2 issue. Let's look at this one, though. The enthalpy for the decomposition of ferric oxide is shown below. What is the enthalpy change for the following reaction? How do these differ? Isn't this one just this one reversed? Okay, so if something is reversed, it was endothermic. What do you think it is now? Exothermic, so it's negative 472 kilojoules. Okay, makes sense? All right, if you have a little bit of room, I'm going to kind of add to this problem, and I'm going to call it 11A. And I'm going to say how much heat is released when we'll just say 4.0 grams of sodium are combusted. Again, stoichiometry. Okay, they tell you how much is associated with that reaction. Well, we start with our number in the problem, 4.0 grams of sodium. What do I convert to? Moles. So for every 1 mole of sodium, I have, we'll just say 23.0 grams. Now I can use this ratio, 4 to that. So for every 4 moles of sodium, I have negative 828 kilojoules. So this would be 36 grams of sodium. So that's the true stoichiometric way to do this. And again, I hadn't covered it yet, but it was in the homework, so some of you who did your homework hopefully got practice with this. Yeah, it wouldn't be grams, because it turns out I'm not looking for grams. This is when I went brain dead. So we're going to do a negative 36 kilojoules. That looks a little bit better because that's what the unit is. Had grams on the brain. Okay, that makes more sense. Okay, let's take a look. This is kind of a thought question. I'll read it and then I'm going to pause and let you guys think about it for a second. It tells you the enthalpy for making water is shown. So notice we're going from gas to liquid, and it's giving off a certain amount of heat. And then we're going here from gas to gas, and it's got a certain amount of heat. Why is the enthalpy change different? Chris got it on the money. In order to go to a liquid from a gas, you have to release even more heat to slow the molecules down even further and get them a little bit closer and to get them to be liquid as opposed to gas. Okay? So here, more heat's going to be given off going to liquid than going to gas. More energy must be released when producing a liquid from a gas than when producing a gas from a gas. Okay? All right, now we're going to, so we've covered our second way. We did calorimetry, and then we did stoichiometry. Now we're going to get to my favorite. It's called the Flippy Thing. Okay? Here we're given 2 equations, and there are delta H's associated with those equations. Please, for me, go ahead and add per mole to all of these, because all of these heats of formation, do you see how these are heats of formation? You're forming 1 mole of each of these from its elements. Heats of formation have the unit of per mole on them, and you can see that from your tables, okay? And these are at standard conditions because of the little zeros. So calculate the enthalpy change for the reaction given those two equations as a resource. Well, this is what I call the goal equation. The goal equation is what we're trying to find the delta H of. So when I start this process, I just start with my first equation up here. Each equation is going to be a sole source of something that the goal has and the goal needs. Okay? Looking at the first equation, what does it have that the second one doesn't offer, which is in the goal? The CO. Notice the CO is a product here and it's a reactant here. So I need to flip that equation. So I'm going to rewrite that first equation, CO going to C plus 1/2 O2. When I flip the equation, what happens to the delta H? Sign changes. It becomes endothermic. Good. Okay, now I'm going to go to the second equation. And looking at the second equation, I see that it's a sole source of CO2. Well, the CO2 is on the product side. There's one of them. Here, it's on the product side. There's one of them. I'm just going to leave that alone. And I'm going to rewrite that equation. C plus O2 makes CO2, and I leave the delta H alone. Yay, happy days. So before I actually do anything with the numbers, I want to add these two equations up and figure out if I'm getting my goal first off. If I'm not, then I did something wrong and I need to go back. So let's check it. What cancels on each side of the equation? The C's go. What else goes? We're cleaning house like we did in electric imbalancing with the redox balancing. So I'm going to take a half out of the equation, leaving me with a half there. So I get CO plus 1/2 O2 makes CO2. Is that the same as my goal? Yes, it is. So because I added those and got the goal, I can now, according to Hess's law, add my two steps here and get my delta H. The delta H standard for this is -283, is that right? Kilojoules per mole. Okay, let's look at the next one, which is a little more challenging. It says use the following standard enthalpy of reaction data. Again, all of these should be per mole. You want to calculate the heat of reaction for the combustion of 1 mole of ethane. A very important point here. How is this different than the last problem? They don't give us a goal. Where's the goal? We have to write it. We write it. No big whoop. Because I just showed you how to write combustion equations. We are going to write an equation where we combust 1 mole of ethane. 1 mole. We got to leave it there. And we actually can do this. So what are our products? CO2 plus H2O. Okay, so I need 2 C's. I always do my O's last. 3 H2s. So that gives me 7 O's on the right. So what do I do on the left? 7 halves. So this is now my goal. La, 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 la. So now we start the process that I just went through with you. We'll start with the first reaction. What is the first equation the sole source of? C2H6. Notice it's a product here, but it's a reactant here, so I'm going to flip it, and I'm going to get C2H6 gives me 2 C's plus 3 H2s. Because I flipped it, what do I do to my delta H? Change the sign to positive 84.68 kilojoules per mole. All right, so that equation's done. So now let's look at equation numero dos. What does it have that nothing else has to offer? CO2. CO2, CO2. Both of them are on the product side, but we need 2 of them, notice? So now I'm going to multiply through by 2, and I get 2C plus 2O2 gives me 2 CO2. Awesome. What do you think I do to my delta H? I multiply it by 2 because this was production of 1 mole. Now I'm producing 2 moles. So it's 2 times the -394. Okay? And then our last equation, we are going to need, looks to me like it's water, right? Water's on the product side. Oh, it's on the product side there, so we need to multiply through by 3, giving 3H2 plus 3 halves O2 to make 3 waters. Just for future reference, if you need to flip and multiply, you can. Okay? Again, Hess's law is awesome like that. 3 times negative 286. All right, so now let's go ahead and check if we reach the goal before we play with any numbers. What can we cancel? Steve's, see ya, get it? What else? 3H2s. I can see some combining of like things here. 2 is actually 4 over 2, right? So when we add those up, we get 7. I'll just write 4 over 2 here up top. So we end up getting 7 over 2. So C2, H6 plus 7 over 2 O2 gives us 2 CO2 plus 3 waters. Does that match our goal? Yep. So now we can go ahead and add up all these numbers and go ahead and just round to 3 sig 1,560. Negative 1,560 kilojoules per mole would be the delta H, standard delta H of this reaction. This is still at standard conditions because we were standard conditions up there.